Look closely at a physical system pushed to its limit, and you will find noise. You see an unpredictable sequence with no discernible pattern. Yet the physical universe runs on strict deterministic laws. Gravity, electromagnetism, and classical mechanics are bound by exact mathematical equations. Here lies a persistent contradiction in physics. When highly complex, deterministic systems iterate, like fluid dynamics or weather patterns, the outputs they generate are observationally indistinguishable from random chance. The observer-dependent theory of everything, or ODTOE, provides a structural lens to examine this boundary between strict rules and apparent chaos. The theory proposes that what we record as noise is not a lack of structure. It is the external signature of an incredibly resilient mathematical architecture. If we want to understand the limits of predictability, we have to recognize that observed randomness is a symptom of deterministic stability. In Kolmogorov-Arnold-Moser theory, dynamic systems face constant external perturbations. Mathematical orbits are continuously stressed, and only the most resilient configurations survive. The greatest threat to an orbit is resonance. If a system operates on a simple, rational frequency, external pulses stack up, amplify, and shatter the structure. To survive, the orbit must be highly irrational, avoiding repeating mathematical patterns that external forces could latch onto. The ultimate defense belongs to the golden ratio, phi. When expressed as a continued fraction, phi relies entirely on a sequence of ones. It resists fractional breakdown completely. Under Greene's residue criterion, an orbit structured on the golden ratio is the absolute last to collapse under chaotic forces. The ratio operates as a physical mechanism. It preserves order against entropy by making the system too mathematically complex to be broken by simple repetition. Consider a physical system continually trying to settle into this highly stable phi-structured configuration. This convergence is described by a Banach contraction. The system zeroes in on stability, scaling down geometrically by roughly 61.8% per iteration. But perfect closure cannot be achieved physically. It leaves an irreducible spiral gap at the center that can never be crossed. Because the contraction can never finish, the system sheds a microscopic mathematical exhaust, a transient factor, with every single step of the iteration. This continuous shedding is identified in the ODTOE framework as the phi residue. This infinite failure to reach absolute geometric perfection acts as an engine. The incomplete convergence pumps out the exact variability we observe in physical measurements. If you stand inside this dynamic system and hold the generating operator, the behavior is ordered. You see a predictable geometric convergence towards stability. Standard observation requires standing on the outside. An external observer records the data without any access to the underlying contraction equations. Without that geometric context, the stream of phi residue contains no discernible periodicity. Stripped of its rule, the data behaves exactly like static. This inverts the standard inference arrow. Deterministic stability, when recorded from a distance, naturally presents itself as random chance. Apparent randomness is an epistemological limit. It is an artifact of the observer's physical vantage point, rather than an inherent quality of the physical world. We can track the footprints of this dynamic in modern physics. In quantum systems whose classical limit is chaotic, the energy levels flawlessly mimic the spectral correlations of random matrices. We see it in Benford's law, where the leading digits of wildly disparate global datasets fall into a strictly rigid logarithmic distribution, and we find it in self-organized criticality. Unpredictable events, like sand pile avalanches, spontaneously align into highly structured, fractal power laws. These are disparate phenomena, yet they manifest the same underlying mechanism. Phi stability acts as the hidden engine beneath the data. The static and noise of reality are not accidents. They are the signature of supreme mathematical stability, operating just beyond the edge of our observation.